All right, we're going to be looking at forces on a box pulled by a rope. So I have a 40 kilogram box and it's pulled along a level frictionless surface by a constant force of 300 newtons. Determine the acceleration of the box. So first, the forces on the box. We have a pulling force to the right. In the downwards direction, we have the weight of the box. And in the upwards direction, we have the normal force. Let's list what we know. We know that the mass of the box is 40 kilograms. We know that the pulling force is that 300 newtons. And we want to calculate A. So looking at all the forces that affect the acceleration of the box in the x direction, the only thing that affects it is the pulling force. So we have Fp equals ma. So we can rearrange our equation, and A will equal our pulling force divided by our mass, and we have 300 newtons divided by 40. Remember, 40 kilograms. A newton is a kilogram meters per second squared, and that's why our kilograms cancel to leave an acceleration of 7.50 meters per second squared. And that is our first example's acceleration. Now, let's add an angle to our pool. So this time, I'm going to use the same mass of the box through these 4 examples, but we're going to change the pool. So the F pool now is 30 degrees above the horizontal. We still have the weight of the box, and we still have a normal force. It is a frictionless surface, so there's no friction. Now, the only component that allows the box to go forward is f of x. If we look at our summation of forces in the horizontal direction, the only force we have is fx, and that will accelerate our system. So we need to determine the value of fx. F pool is still 300. Our angle is 30 degrees. So to find fx, we can use our cosine function of theta will be fx over the pulling force. So rearranging as well as plugging in some numbers, I get fx is equal to 300 newtons times the cosine of 30 degrees. And I'm going to go back and just write that in before I rearranged it. So I had cosine of 30 degrees equals fx over 300 newtons. If you do your mathematics, your f of x has a value of 260 newtons. So that's our only horizontal force. So let's use that to solve our fx equals ma. Oops, let me get a new page. So, to rewrite, fx equals ma. If we rearrange, we have the horizontal force divided by the mass. We calculated fx to be 260 newtons. Our mass is still 40. And we have an acceleration of 6.50 meters per second squared. And that's our acceleration when we hold the rope 30 degrees above the horizontal. Let's look at a slightly different scenario. Same box, same pool, same angle, but this time we have a 30 Newton frictional force. So let's label all our forces. There's our F pool. Here's our F of x. It's still 30 degrees. I'll label the angle. We have weight in the downwards direction. The summation of all the vertical forces will give us Fn, and this time we have F frictional force, Ff, in the opposite direction. Now we do know, well, let's first look at our summation of forces. We're going to look at the horizontal. That's where the motion occurs. So we have Fx minus the frictional force will accelerate our system. So our goal is to know Fx as well as the frictional force. So let's go back and look at our givens. Fx, we actually just calculated. So if you forget where that 260 comes from, go back to example 2. Our frictional force is given in the problem. It's 30 newtons. And that is right here in the problem. Our mass has remained 40. And now we have enough information to solve for the acceleration. Plugging in our values, we have 260 newtons for our F of x minus our frictional force, 30 newtons, equals the mass of our box times A. So A will equal 230 newtons divided by 40 kilograms. And now we have an acceleration of 5.75 meters per second squared. All right, a little less, we have some friction, and we're pulling at an angle. Now, our last one is when you have the same situation, but instead of giving a frictional force in newtons, we have to calculate our frictional force. So this is our most complex problem. So in example 4, we have a 40 kilogram box pulled by a constant force of 30 newtons. Excuse me, that should be 300 newtons. Let me correct that right now. Let me just scratch it out. And 300 newtons, that's a typo. It's applied 30 degrees above the horizontal, and the coefficient of friction is 0.15. Determine the acceleration of the box. Let's label all our vectors. Here's our pull, that's that 300 newtons. It's still 30 degrees above the horizontal. We still have Fx. We still have Fg. We have a frictional force. But we also need to consider everything that's happening in the vertical, and we have a vector, Fy, that's pulling up on the box a little bit, and it's going to affect our value of the normal force. Let's look at our summation of equations first, and then we shall list what we know and start solving. Our summation of equations for our system. It is just F of x minus the frictional force, just like example 3, and that will accelerate our mass. So let's list what we have. Well, I'm going to keep F pull is 300 newtons. We still have an angle of 30 degrees. We've already calculated Fx. That was 260 newtons. We know the mass of our box is 40 kilograms. We don't know F of frictional force. We need to calculate that. And we do know the coefficient of friction is 0.15. So let's think about friction and what we have to do to find that frictional force. And I'd like to go to the next page for this. So frictional force, you know as coefficient of friction times the normal force. But the normal force is really the summation of everything in the vertical. Oops, there we go. So this time, in the vertical, we have the weight, but we also have F of y, and they're acting in opposite directions. So the normal force is going to be less than the weight this time. So to find the normal force, F normal, we need to take the weight of our object minus F of y. So let's determine what Fy is. We can use sine of theta equals, let me write it here, sine of theta equals Fy over the pulling force. So let's calculate Fy using our numbers. So Fy, if I rearrange, is going to be the pull times the sine of theta, which is 300 newtons times the sine of 30 degrees. So we have Fy is equal to 150 newtons. So let's find Fg. Fg is its mass times gravity. So the mass was 40 kilograms, and g is 9.8 meters per second squared. And that is something, there we go, 392 newtons. So we're doing all of this so we can figure out F of n, so we can then figure out our frictional force. So back to our F of n. The weight of the system is 392 newtons minus 150 newtons from pulling up on the box, and we have 242 newtons as our normal force. Going back to our frictional force, and actually I'm going to go to the next page, so go forward instead. Let me write it again. Frictional force is equal to coefficient of friction times normal force. Coefficient of friction was given in the problem as 0.15. We calculated the normal force as 242. So 242 newtons, and the frictional force is 36.3 newtons. So now we know frictional force, we know F of x, and we know the mass. So to remind you what our summation equation is, F of x minus the frictional force will give us the force on the system. Our goal is to find A. So F of x was 260 newtons. Our frictional force is 36.3 newtons, and that equals 40 kilograms times A. A is equal to, if you subtract your forces, you have 223.7 newtons. I'm going to divide it by our 40 kilogram mass, and our acceleration is 5.59 meters per second squared. So finding frictional force when you're pulling something at an angle is a bit more complicated. You have to take care.